Perception of the environment through a camera sensor is getting a lot of attention in the industry of autonomous driving because of the Tesla's decision to ditch LiDAR. In the future lectures, we are also going to start working on point clouds from a depth camera, but before that we need to understand basic camera plugin and its usage in ROS Gazebo environment. We will cover this lecture with these three parts. First, we need to understand topics and messages utilized for camera RGB image communication in ROS. Then we will utilize OpenCV library and its image processing functionalities in our Python nodes. And at the last, we are going to be looking into how we can make changes in the camera sensor of a specified robot, how we can increase the width, height of an image, FPS, and visualize it in RViz. And the basic camera we are going to be using is of Turtlebot 3 Waffle Pi model. Let's see how does it looks like. We will start by creating a launch file inside of our ROS1 wiki workspace and mobile robot package. Here we are going to create it, Turtlebot 3 sensors.launch, in which we will test about all of the sensors, depth camera, simple camera, and LiDAR. A launch file, and here we are going to add other launch files which will bring our robot in the simulation and run some nodes for processing the sensor data. So what are those launch files? Those launch files are going to be from Turtlebot 3 simulation. If I go here, Turtlebot 3 simulation GitHub page, I can see I have Turtlebot 3 fake, gazebo, and simulation for ROS NOETIC, okay, specifically, and all of the documentation is provided on Robotis e-manual website. Okay, what I have done, I have downloaded it through cloning it into my workspace. Here you can see in one of the previous tutorial on YouTube, Turtlebot 3 simulation, fake gazebo simulation, and we are going to be using gazebo package. Inside of that we have a launch file that is just empty Turtlebot 3 launch file. I will run that one, ROS launch Turtlebot 3 gazebo, and press double tap. These are the launch files that are available to me. I will say Turtlebot 3 empty, press tab, automatic complete, press enter. This is going to bring up Turtlebot 3 inside of a gazebo simulation. In your cases, this simulation might not come up, and you have to write this command, export Turtlebot 3 model waffle pi. I have already added into my bash rc file, which is located in the home folder. Press Ctrl H to show hidden files, and in this line you can see I've added into my bash rc file. Whenever terminal run, this file runs and it exports this command. So for our context of the lecture, we have to find out what are the available topics to us. And here you can see we have camera parameter and camera related things, image raw, camera info, compressed image, and a lot of things. We have two cameras in this waffle pi version of Turtlebot 3. Image raw is the one which we are going to look into this lecture, which is basic image. Let me show you. I have to open RViz. Inside of an RViz, I am going to bring in this image topic, and inside of that image topic, you are going to subscribe the camera image raw, which is this specific topic, camera RGB image raw. In RViz, you can see that we have small window which is gray, just simple gray, because the camera it is looking at is this gray world without the grid. So I am going to put some cube around it. Okay, the camera is looking on the other side. Let me put something here, and now you can see a cube here. So there is a camera from which we can obtain a video stream in the simulation, and that's very useful thing. The other thing that we have to look into are these camera info and image raw. If we get information about these, ROS topic info, camera RGB image raw, press enter. It is going to tell us that Gazebo is the publisher because of the camera plugin of Gazebo, and RViz is subscribing it, from which we can see what is this camera actually showing. Other things are sensor message camera. The message of the image is sent under this umbrella. ROS message info, get information about this message. It says there is a header, timestamp, frame ID, height and width, encoding, bigenian, step and data. For our scenario, height and width is resolution of the image, step data is actually the values for all of that. So this is going to make sense if I just say ROS topic echo camera RGB image raw, although it's not going to make sense, but you can see what is printing. This is the data from the images, So that's it from our topic side. We need to now understand how we can get this video and make OpenCV work upon it. You need to keep in mind that this camera is only specified for Turtlebot 3. It is not a general camera for all of the robots available in ROS ecosystem. Let's now deep dive into creation of node for a camera image subscribing and applying OpenCV functionalities. So let's start writing a node. But don't forget this launch file. We will fill this at the end of this lecture. If we go into learning package, in the source file there is a node that can help us and we do not need to write it from scratch. Let's paste it and start making changes inside of it. If I run the simulation, ROS launch turtlebot gazebo turtlebot empty world ROS topic list. So if you remember, we had a lot of topics and the topic in which we were interested is this one, ROS topic info, and this one. This is the message type it is utilizing. So let me bring my node. I want to deal with not the geometry message. I'll delete that. I'm just going to say import. What is the message type? Sensor message dot message and import image. This is the data type used by this specific topic, so when we will subscribe it, we will be needing it. The next thing is the node name is not turtle sim, it's sensor check. ROS Pinet node name, it's not velocity manipulator, it's sensor checking. This class is called, which we will write here, and that's how it is going to work. Camera callback. Let's make it bigger, and we are going to make a lot of changes. We are not dealing with the publishers, we are only dealing with the subscriber topic of camera RGB. In subscriber topic name, we are going to bring in camera RGB image raw, and we don't have any publisher. So number subscriber, or we should say camera subscriber, it is going to be getting the subscribe topic. It is not pose, it is image, and you are going to go inside of camera callback. In camera callback, I would say data, which is going to be obtained and processed. What are the other things that we need to create? First, there is an out object which is going to save the video, and the other one is going to be bridge object, which is going to create a bridge for ROS image and CV2 required image format. This one is going to be really simple. I'm just going to say from CV bridge import CV bridge. This is a function that is going to help us in the conversion part. Whenever we talk about CV bridge, we need computer vision. So we have to just say import CV2, which is going to bring OpenCV into this code. The out is going to be a function of video writer, which is going to save a video at my home folder with output.avi as its name. This is going to be its encoding and 10 frames per second with 6040 by 480 resolution. Bridge is going to be simply CV bridge object that is going to create the bridge. This is the object of CV bridge. Let me show you how it is going to help us. So let's start manipulating the data. Frame is going to be equal to self.bridge object, and inside of bridge object we are going to convert image message to CV2. This data message is going to be given as an input to this function, that is CV bridge object, which is then converted to CV2 required format. And then we simply say self.out object that we created, we use it to write each frame. Then we can also visualize it with the most popular OpenCV function IMShow output, and we visualize the frame that we are writing, cv2.wait key. It's now time to run this node, but before moving forward we need to rename it properly and say camera sensor. That's enough, and it should be of proper spelling. That is going to be the node. We will be writing image stream into a file. ROS run mobile robot package. Its name is camera sensor. Let's see what is the output. You can see an image show video that was previously shown on ROS. Let me put something in front of it and bring this output video, which is of CV2 library, so we can see what is happening. If I put something in front of the robot, it is apparent there, and that's how you can utilize all of the CV functions. If I stop this node and go into my home directory, this output.avi has been written, and you can see it is sort of recorded. What else can we do? we can apply a lot of things. We want to see a frame, but before writing it out, we are going to say edge frame is equal to cv2.cani, a function that performs conversion of whole image into binary image, which can be utilized to extract the edges. We are going to input the frame and some thresholds, just generic number. We are going to image show this edge frame. Let's see how does it looks like. And as we have an object in front of it, you can make some changes with it. Let me bring it here. There is no edge. If I put something while keeping it on top, if I put something far away, there is a ball, there is a square, and there is this thing as well. Edges of the objects in an image are perfectly extracted. Although this edge thing is not being captured in the video, in the output it's simple frame that is being written. Okay, and that's it with the code for OpenCV and camera system. And this is one example what you can do with OpenCV and ROS. You can do tons of a lot of other things, but this is not a computer vision lecture. Let's keep it simple and let's move to the next part, which is going to require your effort for understanding XML syntax, but very useful parameters to change how our camera plugin behaves in the environment. So the question is, if we want to make changes into the resolution and the FPS, what are we going to do? If we are looking at something like this package Turtlebot 3 simulation, which have the launch file to bring in the Turtlebot, we are going to get this launch file. And in this launch file, you can see there is nothing mentioned about the arguments for camera properties. In this Turtlebot 3, there is a folder named as model, and that contains Turtlebot 3 model SDF file, 3D files. But we want to access the URDF to make changes in the camera sensor properties. There might be some node of camera info, but still we need URDF. And that URDF is present on this link, Turtlebot 3 Robotics GitHub. This description package is one that contains the actual URDF of your robot, and it's a generic style of describing your robot. So there are a lot of things, common properties and burger, auto race, waffle pie and waffle URDF. We are going to obtain this one, but first we need to delete the package that is installed in our system. As you can see, Turtlebot 3 simulation only contains fake gazebo and simulation. There is nothing as Turtlebot 3 description. So what we need to do, sudo apt purge ROS NOETIC Turtlebot, double press tab, and we have Turtlebot 3 teleop, Turtlebot 3 fake messages and another. Previously I have more options as well, but I uninstalled all of them because I was interested in downloading them manually by cloning this repository on my system and extracting this description package. It is here being cloned and it's done. So I'm going to go inside of this package, which is Turtlebot 3, just going to extract this Turtlebot 3 description, which is this one, and I am going to bring this into my ROS1 wiki as for the purpose of this lecture, because for only one reason. We want to make changes inside of this description and URDF specifically for our robot, that we can actually see what are the settings available. So if I perform ROS launch Turtlebot 3 gazebo and empty world and Turtlebot 3 empty world, press enter, it is now going to access Turtlebot 3 from this specific package, not from something that is being installed in the lib directory of my ROS installation. So let's make some changes. As our robot is waffle.py, if we take a look, Turtlebot 3 wafflepy.urdf.zacro, Turtlebot 3 wafflepy urdf.zacro, this file is called. And if you go into this file, it contains, if I press Ctrl F to search camera, we have this camera. Where is the camera plugin? There is no camera plugin here. Let's find out in this one, common properties. If I open up here, these are just colors for gazebo. Let's open Turtlebot 3 gazebo.zacro, this one here, and I think so we can find it here. Yes, Turtlebot 3 controller is here, IMU plugin, laser scanner plugin, camera RGB plugin. So we have here depth camera controller and simple camera as well. OpenConnect. Okay, so we are going to look at this one first. If I go into the simulation, run it, and then if I want to get actual size of my image data, I don't write it down. I just say the frame that I am getting, I want to get information about it. Print frame dot size to get information what this is actually doing. Let me just print out frame, and I am going to run ROS run mobile robot camera sensor. Let's see what is the size. It's 9:1,600. That doesn't make sense. So the change that we have to do is not size, it's shape. Let me run it again, and we have 480 by 640 by 3. So this is the dimension of this image that we are receiving. It's not defined here, it's inside of the sensors. But the point is, if we look at here, it is 1920 and 1080, but we are getting an image of 640 by 480. The problem is, this is Turtlebot 3 Waffle.gazebo, and our model is Turtlebot 3 Waffle Pi Gazebo. So here you can see it's 640, 480. If I make the change here, like the one we have in the Waffle, 1920 by 1080, 1920 by 1080. If you want to get more resolution, I am just going to close the simulation. Isko cut kar dena, quick kar dena, and run it again. Now we have changed the resolution for the camera sensor of our Waffle Pi that we have. And let's now run this node. And now you can see the resolution has increased a lot. But the important point is, it has now changed for the simulation. So this is what you can do for the sensor values that you want to manipulate and make some changes. If I want to just say there is an argument for it, meaning if we call this file, you can make the changes here. If I set directly to true with an argument, that's more appropriate in the Waffle Pi Gazebo, you can actually visualize the camera in the simulation. That's a very, very useful parameter to set. Let's rerun it, and you'll see a camera in the simulation for our robot. So here we have a camera, although it's not very apparent. This one helps us a lot in the direction of which the camera is looking at and what the camera is looking at. And sometimes we don't even want a node or ROS to see what the robot is looking at. So this visualize to argument is really useful. And there are a lot of other things that you can do. Let me undo it. The proper way is to set this to be true whenever this file is called. Other things that you can do, starting from 0.03, let me make it 500, very big, and starting it from 1 meter. You can change the format, but I don't want to. Horizontal FOV, field of view, horizontally, if I increase it to 10, which is way big, and I now run this simulation. My computer ran into problem with such settings. These values are way too much, so I'm going to set back into true, and 5 would be fine, and 50 far away would be good. Save the file, run the simulation. Now let's see what our robot is looking at. It cannot look at anything which is under 1 meter. So it cannot look at this thing. If I bring it here, it can't even look at it. It's looking at far away. Now at this specific point, it can look at this cube, and now it is unable to find this square. So basically you can do a lot of things. One more topic that can help you, ROS topic list. If I get into this thing, ROS topic info, camera RGB info, ROS topic echo. What this tells us is simple mathematical model for the camera that you are using in the simulation. Distortion, some constant, you can look into the wiki, binning, offsets, and other properties you can change for your specific requirement of a real world camera that you want to simulate. These are the main parameters or settings for the camera that you can do. And for this specific Turtlebot 3, you must be very careful about Waffle Pi and Waffle Simple. This is one small portion that you can do to fit your simulation according to your needs. One last thing that we need to do is to set up this Turtlebot 3 sensor.launch file. We want to include first the launch file that brings in the robot, and after that we need to run the node that is going to run the computer vision node. Mobile robot is the package name. It's going to be camera sensor, and the type is going to be camera sensor as well. What we have to do is to set up an argument, because in the next lecture we are going to be adding another sensor. We need to set an if condition around it, and that if condition is going to be talking about an argument, because we have multiple sensors in the future lectures. So if you want to see the camera sensor, we are going to enable this argument. Otherwise we are going to go with another sensor that we have, that is going to be LiDAR. So argument is going to be camera enable, which is going to be set up here in the start. Argument with the default value camera enabled, its value is going to be false at first. So it's false, camera enable false, it is not going to run. The next lecture you will understand why I have this LiDAR enabled, and similarly we will have another group that is going to use this argument. It is going to be LiDAR sensor, and the output file is also going to be this. It's a Python file, so we need to mention it. Coming back to the important question, how to bring the Turtlebot whole launch file. We are inside of Turtlebot 3 Gazebo, so the package name is Turtlebot 3 Gazebo, and inside of that is a launch folder, and inside of that launch folder we have this launch file. So let me run this launch file. ROS launch mobile robot Turtlebot 3 sensors. Double press tab. It has two arguments. Camera is set to true. This runs the launch file, and it also prints out an output from the node that I have. So that's basic setup that we will be running again and again directly through this launch file. And that's it for the camera sensor. But keep in mind, possibilities are endless. I have not given you some real world examples in this lecture, but let me just tell you, me and my team had a project of self-driving car in a gazebo environment with ROS. And we built it with one single camera, no depth cloud, and the car was falling. You can search it, self-driving car mini Tesla Noshlook 2 on GitHub. What you need to take out of this lecture was understanding of camera plugin. That's very important, because upcoming lectures are all going to be about different sensors and going in deep understanding of depth point clouds.